Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So we have been talking about friction alleviation using combined motion. So last time we discussed about different problems and like how we can remove a cork from a bottle. So we combine the motion and then because of that the direction of the friction force changes. So the effective friction force which is required against pulling the cork out, that will get reduced. So I think continuing in the same direction, um, this is what I'm presenting here is part of my PhD thesis, and we combined that approach really well with respect to flexible instruments and for medical application. And if you are looking for catheters, endoscopes, and suppose we want to navigate or want to place those instruments precisely and want to get rid of any kind of unwanted motions, how we can get out of those problems. So we wanted to maximize the motion and force fidelity. So whatever is the input and what we are getting at the output, how we can increase that fidelity, that transparency. I think that was the approach. So if you just look at it, the instrument is modeled as a beam. So just think of instruments and suppose if you are pushing and this is the tube. So like this can be the channels provided in the endoscopes, or it can be some channels provided in the support structure, the endoscopic platform, or even in the catheters we have. So, this instrument is very flexible, so it interacts to the wall, but then it comes in physical contact, and because of the friction and these instruments are very long, so slender structure, and then because of the friction, when it interacts, we'll have many issues, and there can be some jerk kind of operation also, or sometimes it gets jammed as well, or there will be stick and slip motion, there will be sudden movement, and or it will get jammed. So that is something not desirable, but we cannot get away with the friction problem. So suppose if we want to work in this kind of scenario and just wanted to see if we combine the motion, uh, can we improve the performance, or in a way when we talk about the precision, can we get that? So if we just concentrate at the tip and if you are moving, pushing from this side, so this is the motion input, what we realize that okay, there are like triads defined. So this is along the direction of the tube, and then is the circumferential direction, and then another normal binormal defined. So we get E1, E2, and E3. These are the unit vectors defined at the contact point, and of course with respect to the tube walls. So this is the instrument. So now we enlarge and suppose it making contact at P, and suppose at this end you are pushing and at the same time you are also rotating. So at this end what you are getting is, so there will be, suppose this is the axial direction defined. So this is the pure translatory motion VA, and then you have this E3 defined also. So because of this, there will be circumferential motions and then a normal. So okay, Vn and ultimately this V and Vt defined, and the friction force is against that uh, opposite to the resultant slip velocity that will be applied. So to make it more precise, or if we just look at this diagram, I think it's a better representation. So just we can call it a tangent plane at the point of contact P. So it's making contact at P, and EA is the, so this is my VA. So this is how the instrument is posed. So this is the interaction, the forces acting. So that's why you have along the axial direction, you have this VA defined. But when you combine, so maybe just to have this line, you can say omega, the rotation of the velocity, rotation, the angular rotation of the instrument, and multiplied by r, radius of the instrument, and this can, we call it Vc. So this Vc is there, so Va and Vc. So now two motions are there. So when we have, so if there is no rotation involved, you will have only Va, but when rotation is involved, and suppose Vc is the velocity on the tangent plane, so effective velocity, the slip velocity will be Vt, and therefore the friction force, only the direction will change. So your friction force is mu n. So the magnitude, of course, it depends on n. Mu we are assuming is a constant, but the direction will change because the slip velocity, the direction of the slip velocity had changed. And what we realized, because of that, there is an angle between the axial direction and the actual friction force, and this angle is defined by phi. And ultimately the force in along the axial direction, you can see that is only the component in that direction. So from the figure itself, you can see that it has reduced, and is simply the cosine component of the Ft. So moving on. So if we so this is the tangential velocity, and tan phi is Vc by Va. Vc is the circumferential velocity, slip velocity, because of the rotation, and Va is the axial velocity. So if we try to write the friction components and the values, yes, at point P, Ft is still same, the friction force mu Fn. Only thing is now direction has changed, right? So it's opposite to your Vt. So if we try to see what is the friction force along the axial direction, so this is Fa, that is the component along the axial direction, which is nothing but the cosine of the the net friction force Ft. And if we substitute, what we realize that is a mu Fn cos phi. And suppose if we just want to define some kind of effective mu, although mu has not changed, but suppose you want to define some kind of effective coefficient of friction in that direction, we can simply write in terms of Fn. So here mu effective will be simply mu cos phi, where phi is defined by this tan inverse Vc by Va. So I think modeling wise is a very simple model. The mathematics is also simple, so it's not so complex. If you are able to visualize, I think it's very easy. So, if we try to see what is the effect on the force transmissibility, and then we can define the reduction. What is the reduction in the friction force? So, because of the combining the motion, two motions, so axial versus the rotation, and of course, it's initially is a ft. So, the reduction will be 1 minus cos phi, and the effective coefficient of friction we can define, which is mu cos phi. So, what we try to do is we try to define some parameter and try to find some relationship so that we can easily represent it. So, if you look at the capstan equation, so this is forces on the slack end and the tension end, and when it's passing through an edge, so or passing through a wedge having an angle alpha. So, this can be considered very similar. So, it's making an angle alpha, and mu is the coefficient of friction. So, mu and alpha is there. So, the ratio is well defined. F in by F out is simply e to the power plus minus mu alpha, depending on which way we are trying to move. If we take the log of this, we simply get mu alpha plus minus mu alpha. So, when it's simply translating and translatory motion is there, we can write in that way, and when we combine, we just write in terms of mu effective, and alpha is still there. So, now the right hand term is very simple, and so what we did is to compare the two transmissibility in a way. What we can say, we defined a parameter, so a ratio we define, and to compare the effect of your combined motion on the force transmission along the axial direction, and this is how we define zeta. So, log of the forces combined versus log of forces when there is a pure translatory motion. So, on top when it's a combined, at the bottom in the denominator is just the when it's a pure translation. And what we realize that ultimately this is very simple, and this zeta value is simply cos phi, which is a function of the combined motion. So, Vc versus Va, and we can also write in terms of Vc by Va, and this turn out to be, because tan phi is defined as a Vc by Va, so then we can write cos phi similarly. But we find a very simple formulation. This ratio turns out to be simply cos phi. And analytically also we try to simulate and try to find that if so we have translation velocity, so in the instrument, so this is Va. So, like plus minus direction, we are simply translating back forth with this amplitude 5 millimeter per second. So, this is what you see, the blue line. So, plus minus, and then we just added the sinusoidal rotation motion, and then we have the theta in dot, and we can get Vc also, what is the combined motion, and then we superimpose. So, these are the velocity inputs. So, Va, and this is corresponding to Vc. So, the circumferential velocity. And what we realize as the rotation part, the amplitude, so it increases. As it increases, the effect is more pronounced, and for that reason what we realize that zeta value is is there is a significant reduction in that value and is approaching towards zero value. So of course it will never reach zero, but you can see that from here, from 1 it's coming down. So significant reduction in friction force along the axial direction if the axial velocity is combined with the rotational velocity. So yeah, from the model this is what we got. And of course we also need to verify different kind of parameters. So in this project we also try to develop different modules. So we have the actuation module here, and for the measurement we have non-contact kind of measurement here, and for force sensing when the instrument is interacting with the surface, with the wall of the channel or the tube, whatever you can say, we want to measure those forces precisely. So we develop a force sensing module there, and so definitely I'll talk about these designs later in the lectures, and then we maybe will able to appreciate what goes in when we are trying to look for higher precision or repeatability. So again, it's a 6 degrees of freedom force sensing module, and we use wire flexures, just thin wires, and then how precisely the forces can be resolved, and then we can measure. On the other side, for the tip measurement, we use this non-contact type of measurement, and we use a very nice cam, I would say. So although it's not touching, but and it's only the linear displacement we are measuring, but we can convert into rotational rotational measurement. So we can measure it, and at the same time, if you see this block, this is supported on air bearing, so that we can get rid of any kind of friction related issue. So we try to use all the principles, or we can say most of the principles used to design precision systems. So when we started doing the actual measurement, we can see that when we combine, so when it's there is no rotation, is you can see that is at 1 plus minus 1. But when we are combining cos phi, the dotted line you see, you can see that the output is somewhere there in all the cases. Of course, you can say that there is a lot of variation and vibrations. In this case, it's not a rigid system. We are talking about long, flexible instruments, maybe of the order of a meter, and then the flexibility, the torsional stiffness, and the bending stiffness. A lot of clearances involved. So, although we try to pre-tension it so that we can get rid of certain problems, but even then, because of the length, it's a highly compliant system. It's not a rigid system, and therefore we see a lot of variation and a lot of vibrations, and which is good because we may want to we don't want to see a very clean data, because uh, otherwise it will look wrong, and the modeling, of course, we assume that is perfectly rigid, and we are not assuming that it has limited stiffnesses. But so it's good that we can capture all that phenomena. But I think at the same time, what I also want to convey that if we can introduce these methods, and we can design systems where we can precisely predict, I think that will add a lot of value to the concept and to our understanding. So, but nevertheless, we were able to see that there is a reduction in the forces in the axial direction when we combine with the rotation motion. And there are other examples we have discussed in the course, and we can refer to the book also. There are very nice examples given, and it's a use for different application, for fabrication, for positioning, for accurate positioning while machining. And because in machining also, and when we are fabricating something with the tolerances in a submicron level, then even the clamping forces can introduce a lot of errors. So how to clamp it, how to hold it, so that those things can be avoided. So very good examples given, and I, I would encourage everyone to refer to the literature, refer to the books, and if time permits, definitely we'll discuss those cases one by one. So moving on, so what we realize that, of course, if there is a direct contact and there is a sliding friction involved, there are a lot of issues, and we talk about the hysteresis, and we also try to find ways to alleviate friction related problems. Nevertheless, there means even if there is no apparent motion, there can be still hysteresis, and that happen because of the micro slip. So we don't see it, but because of the nature of the joints, we will find, or we encountered hysteresis, and moment we have a hysteresis, we'll have a positioning accuracy problem. So for instance, if we take this case, the clamp joints, so suppose if we clamp this thin part, you can assume a flexure also, and with the rigid block, so we can say the clamps are infinitely stiff, and same coefficient of friction you have, and even the clamping, this forces what we have clamping with. Uh, so what we realize that even though it's well distributed, we can still have hysteresis, because this force transfer, if we apply force F and moving forward and backward, so if there is a reversal, what will happen, that this force transfer is happening. So yeah, means it's like this, right? If we try to get the load path, and at the junction where it's a clamp, what we find that there is a slip, and this force transfer is happening because of that slip. And what we realize, that as we move, and there will be reversal. So this, as we discussed, when we have two masses connected with three springs, we talk about the slip front. Here also there will be slip front, and as we keep increasing the force, that slip front will keep moving towards left, and the entire region, entire block or entire member undergo a deformation or deflection. But since there is a differential, I would say the distribution at the clamp point is not same, so there will be some slip, and that force transfer will happen because of that micro slip. And moment there is a sliding motion, so although it's happening at micro level, and that's why we are calling it micro slip, but that will lead to hysteresis, and it means we'll have a problem with the positioning. There will be positioning errors. So a lot of design rules or design guidelines, wherever we have this kind of clamping, and we want to put the things together, and if the load is either in tension or in compression, or whether it's in rotation, the torques are applied, how to take care of that. So as we said, that hysteresis in mechanisms or in a structures frames, that is detrimental for precision. So that's why it's very important to understand. So in this case, if we are talking about the structures and weldments, so suppose this orange part welded to this frame, what will happen? So the key point is, if the stress distribution is very large, so in some places we have a high stresses, but in some places it's a very small, what will happen, there is a gradient, and so once welded and when it's like coming to the normal temperature, so there will be shrinkage. So because of that, there will be uncertainty involved, because again the micro slips are happening at the end, and which will affect the accuracy of the positioning accuracy of the parts. So what is then desired is, we should look for high surface pressure or no contact, and this is what we observed in this case. So larger area, and larger area means large deformation, and so we can have a very high stress distribution, but at the same time low stress distribution, and they will try to spread over, and this is not good. So what is mentioned, prevent material surfaces too much outside of the weld. So we should try to prevent. So this is, in terms of precision, not very good, and that's why what is preferred is a whole weld or a small contact area. So for instance, in this case, these two cases, what we realize that now is restricted to a smaller area, and so there will be high pressure, and in most of the things there is no contact. So there is no contact, no sliding friction involved, so there is no micro slip, so we can get rid of those issues. And similarly here also, what you can see, so these two are preferred choices. So be aware of that. Similarly, in the structures, we also use a lot of bolted connections, also for positioning, and it's the same thing here, a larger area here, and stress distribution. So again here, it's bound to have happen micro slips, and the positioning accuracy will be difficult. So what is preferred is high surface pressures, and then you are talking about the washers here, and then clamp it so that it's a predefined. The stresses are like concentrated and defined along the washers, so predefined, and there is no contact in these regions. So well defined small contact zones for high contact stresses, and definitely if we have this kind of thing, we can prevent hysteresis, and thus we can achieve better precision. That is for one contact, and when we want to transfer the load or the forces, but many times we will be also we have to deal with the torque transfer, and one may not be enough, but we may have to put at least two, right? Two of these connection points are required, bolted, and of course, because we want to resist this moment, so we try to put them fast so that the forces are small there. So of course, with respect to torque transfer, it's a good, but no matter how good are those bolted joints, if there is any change in temperature, and if there is any thermal load, what will happen, there will be some differential change and some deformations, and we cannot avoid those contraction or expansion, and because of that there will be some movement. So of course it's over constrained design, so that will lead to issues, and sometimes because of these um, small deformations or small differences, the bolts can shear as well, so not very good. So the best way is simply make a cut here and then make a elastic joint, or uh, make it deform. So if there is any change, this body will deform and readjust. So there will be no slippage or micro slip or any kind of movement at the bolted section, but it will just absorb, and that is the beauty of compliant mechanism. So wherever possible, if you provide that. So in order to address over constraint related issues, many times the compliance can give a lot of solutions. So here, as we are saying, the shrink absorbed in deflection rather than contact slip. So here is a slipping, but in the other case it's just getting absorbed by the elastic member, and that way it will also not affect the accuracy of the system. So if we really want to have a free of hysteresis clamping, so going on the similar line in one plane, if you make a groups, and for the other direction, this is the side view, then make a groove on the perpendicular direction, so two series of grooves. So at the bottom, if you see, is more like with all the slits, and these are more like individual members. So that's why we are calling it nails. So it appears as is a bed of nails, and then we are clamping it. So what is good about it is it can move in this way and this way. So if we just look at it, it can have this slight movement and it will be elastic. So what is saying, the contact surface of the solid here can make slight in plane deflections. So these deflections are now possible, followed without micro slip. So they can, because these are elastic members, and if they have to accommodate any kind of deviations because of thermal expansion or contraction, they can easily accommodate. There is no need to move it entirely. So without micro slip, and if there is no micro slip, then the hysteresis will not happen. There will be no hysteresis, and therefore the repeatability will be always better. So this is another concept which can be used wherever we are looking for precision, but at the same time there are thermal changes, there is a change in temperature, and the variation is there, and how to accommodate that. So again, very nice example. Of course, here the length and the width of the each nail, that is important, because if it's too long, then because it's a compressive load and it has to be preloaded. So we have to take care of that, and of course, whenever we are designing things using compliant mechanisms, we have to also know the limitations and we have to check for that. So for instance, if you are designing clamping for the flexures, how to design that. So here is not symmetrical. So if you want to make a symmetrical clamping, then we can have a whole flexures on the either side, so that when we are clamping, it will deform at these points, and then we can provide a similar clamping here. So we can assume either a sheet flexure or wire flexure if we are trying to clamp. But again, here there can be some micro slip, and if you want to get rid of that, we can use the concept of beds of nails. So this flexion member individually, and then it's a compressed preloaded with that, so that whenever if we have this force, there will be elastic deformation here, and if it's elastic deformation, it can be always restored. So we can see that there is no hysteresis, but a clear uh, characteristic, and it follows the same line whether going upward or backward. So again, very good concept if you want to clamp. So one of a very interesting topic, and is there because of the friction. Um, and many times when we start and when we are discussing about controlling degrees of freedom, we are talking about the stops, or we are talking about the contacts. So support on these kind of surfaces. So why, although to start with this a very nice concept, but then because of the friction there are a lot of issues, and we have to be aware of that. So what happens when we are using these kind of stops for positioning? So very simple case, if we check this and try to slide this orange block on the surface, so because of mu we can also define alpha, which is smaller than this mu, tan inverse mu, that angle. So if it's very small, then okay, we can say more or less it's a mu. So if it's within and force is applied, what we realize that it will get jammed. There will be self-locking when alpha is less than mu. So if you remember, this is mu. So cone of friction we can define. So if the force, the direction lies away, then it can move, it can slide. But if it's within, in this case it's within, right? This is the friction cone, but the force is inside. So no matter how large is the force, the friction force will be even larger, and it will be always more than F sine alpha, and that's why it will not move. So it's just the friction which is holding it. It's a self-locking. So if we just extend this, and suppose in 2D case, if we try to position again these three stops, and we want to know what is W1 and W2 or N, what will be the values, and okay, what will happen. So for instance, at least this, because of this W1 and W2, the friction force will have this virtual play. So every time we take it out and move it back, although we are saying it should go to the same location, but what we learn that if the object has a limited stiffness, the stiffness C, and if the friction is involved, although there is no gap, but still there is uncertainty. So there will be virtual play. And it means one cannot say about this n, because there is always some uncertainty. And so there is even though all three are in contact, but this is the uncertainty in positioning. If the force, this alpha we are applying, and which is below mu, actually it will get jammed, it will never come in contact with this. So no matter how large is the force, and we may feel that is touching the third point, but there is no contact there, so it can also get self-locked, and yeah, the error can be very large. So friction can cause position errors or even self-locking, in very layman terms. And if we try to understand, and so the principle of self-positioning, I think we have studied this one, and we cover when we're talking about the calculation of nesting force window. And one of the thing what we do is, suppose these are the three contacts mentioned, 1, 2, 3, these are the three forced, how to find that nesting window. So first thing is we try to determine the poles and nesting torque direction. So, for instance, in this case N1 and N2, so P12 that is the pole, assuming 1 and 2 is in contact, and in order to make the third contact, this is the direction of the nesting torque required. And if you want to achieve that, then any force, whether it's a sufficient, so if it's whether it's passing through that point and just little away with that epsilon, you can see that the torque is sufficient, so it has to lie on this direction, so that we get this P12, the torque at pole 1 2, that 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 way, and that's why it has to be shifted to right. Likewise, we can all determine all the poles. So, like P12, this is for 1 and 3, and of course 2, 3 they are meeting in the infinity. So, this can be the a torque or force what we can see, right? So, these are the poles towards the infinity, and then we start eliminating, or what we start to find the zones which are prohibited. So, if you look at these forces and P12, what we realize that this zone, if is crossing, so Fn, if you are talking about, we just deviate little bit left, right, up and down, what we realize that which one is good for us. So, what we realize that this shaded region is no, because it conflicts with the requirement, our requirement. So, that is prohibited zone, and one by one we can also find. So, similarly we can find this is not good, this is not good, right? Of course, what we have to understand in this case is there is no friction involved yet, and therefore what we know that the any force which is along not touching the prohibited zone provides the good solution, right, Fn. So, this will be the one solution. Other way is also R1, R2, R3 reaction forces we can, and then combine, and we can get Fr also. We can also make certain assumption that all the reaction forces should be same and equal, then also we can do this, because it's only 3 force member and we should be able to find it. So, that is the alternative, find Fn on the basis of equal pin reaction. So, this is Fc all same. So, if we combine these two, this is what we get, right? And then if we extend these two forces, and what we realize, this will be my actual nesting force requirement. So, again, there is no friction involved here. So, very clean picture. What will happen if mu is not 0? So, all these diagrams what we have, actually it will also change. And for instance, if these are friction cones, mu, because of mu you also define the shaded region, and what we realize for this part, this is again known. So, and ultimately what we see that this will also get modified. So, this section will get added. So, it's a prohibited. So, ultimately what we see is it has enlarged, and no wonder if we find no solution for certain cases. So, it means then we have to work out, and then maybe we have to find the or we have to do the repositioning of the pins. So, the idea behind showing all these examples are friction really complicates the design, and sometimes we may not have a solution. So, things can get jammed or locked, and therefore we have to be aware of those issues. and if not, then try to find ways to minimize the effect. So, of course, we have been discussing about it, and in the beginning of this uh, lecture, I would say this in the previous lecture also we talk about friction and the hysteresis, and in the beginning itself we said why compliant mechanisms, and now we see why. So instead of the solid supports, we can also use compliant pins here supported, uh, so that if there is any, so we don't have any slip here, so any deformation it will be in the compliant mechanism. Of course, we have to make sure that the deflections are small, and what we also learned that if we take just one compliant member or a strip or the leaf spring, so it's a 1/3 from the this one and 2/3 from the end, so it will be equivalent to a kind of a spherical ball with that kind of. So be aware of that, and accordingly we can design. But yes, the compliant systems, compliant mechanisms can always to the rescue and can help. About the nesting force, yeah, it's very difficult to get the precise direction, or so if you want to have a well-defined line of action for the nesting force, we can use this kind of wedges with these rollers, and then can have, with the help of a spring, we can, so that it readjusts on its own. Of course, this looks very big compared to this block, so this is mainly for illustration. It can be just hidden on the one side. Yeah, farther this one, these distances, actually this will also add to, because ultimately there are friction involved here, and that will also lead to positioning errors. So we may try to avoid like how far they can be. So we try to restrict within a certain zone, and we can even think of using flexures for loading. So yes, we stop here, and this topic we conclude here. Of course, there are many things, and friction is something difficult to avoid. We try to minimize, and we try to find different ways, different means to avoid friction. But even if there is a friction and clamping involved, what are the techniques, what are the design rules? We can always refer to this book, Design Principles for Precision Mechanisms by Professor Summers. The Dutch version is by Professor Koster, and it's, it's widely used in Netherlands for designing machines, precision for precision applications for semiconductor industry. I'm repeating it, but that's how it is, and whether it's a mechatronics or precision application, that is something which is to the core of the mechanical design. And again, it's originated from Philips, and that's how it has started. Third, fourth generation now teaching, and of course, this is my work and what I did during my PhD. So you can also refer to this if you try to see some examples, and how that can be used to design devices or mechanisms for precision applications. So uh, we'll stop here, and from next lecture we'll take up new topics. We'll talk about non-contact bearings, different kind of actuators, and dynamics, and we'll also take up some more examples. So let's just stop here, and continue from the next lecture. Thank you.